Welcome to your comprehensive interactive study breakdown on the rate and extent of chemical change. In this topic, we'll explore how fast reactions happen, how to measure and control that speed using collision theory, and for higher tier, how reversible reactions reach dynamic equilibrium. We'll also use Le Chatelier's principle to predict how changing conditions affect the balance of products and reactants. Let's dive into the core concepts that are essential for your GCSE exams and for understanding industrial processes. Let's map out the core ideas. First, reaction rate tells us how quickly reactants turn into products. Collision theory explains that for a reaction to occur, particles must collide with enough energy, at least the activation energy, and correct orientation. We can increase rate by raising temperature, concentration, pressure, or surface area, or by adding a catalyst. For reversible reactions, a closed system reaches dynamic equilibrium where forward and reverse rates are equal and concentrations remain constant. Le Chatelier's principle allows us to predict how equilibrium shifts when we change conditions. For example, increasing temperature favors the endothermic direction. Turning to our core study notes, the mean rate of reaction is calculated by dividing the change in quantity of reactant or product by the time taken. For a reaction that produces a gas, we can use a gas syringe to measure volume over time, or measure mass loss as the gas escapes. For example, if 50 cubic centimeters of hydrogen gas is produced in 20 seconds, the mean rate is 50 divided by 20, which equals 2.5 cubic centimeters per second. Always include units in your answer. Here's the experimental process for measuring reaction rate. First, set up your apparatus. For a gas-producing reaction, connect a flask to a gas syringe or place it on a balance. Start the reaction by mixing reactants, then record the volume of gas or mass lost every 10 or 20 seconds. Plot a graph of quantity against time. The slope of the tangent at any point gives the instantaneous rate. Initially, the gradient is steepest because reactant concentration is highest. As reactants are consumed, the rate slows down, shown by a decreasing gradient. Catalysts keep the rate high for longer. Let's work through a typical 6-mark exam question on Le Chatelier's principle. The Haber process is exothermic in the forward direction. If we increase temperature, the system tries to oppose this change by absorbing heat. It does this by favoring the endothermic reverse reaction. Therefore, the equilibrium position shifts to the left, decreasing the yield of ammonia. Remember to state the direction of shift and explain using the principle. Watch out for these common pitfalls. First, don't confuse reaction rate with equilibrium position, they are different concepts. Rate is about how fast, yield is about how much. Second, catalysts increase the rate of both forward and reverse reactions equally, so they never shift equilibrium position. Third, Le Chatelier's principle applies only to closed systems where nothing can enter or leave. Finally, when describing dynamic equilibrium, always mention that it occurs in a closed system. These tips will help you secure full marks on exam questions. To wrap up your revision, remember that reaction rate is calculated from the change in quantity over time. Use collision theory to explain how factors like temperature and concentration increase the frequency and energy of collisions. For reversible reactions, dynamic equilibrium occurs when forward and reverse rates are equal in a closed system. Le Chatelier's principle predicts how equilibrium responds to changes in conditions. Catalysts speed up both directions equally, so they don't alter the equilibrium position. Master these concepts to ace your exam questions.